Welcome back to our engineering mechanics lectures, and now we're looking at our next topic, which is actually a continuation from before, where I want to talk about parallel force components through the so-called scalar product. And the reason this is a continuation is really because we are looking at a method that can be used to determine the angle between two vectors. That is where we left off our lecture last time when we talked about position vectors, and now we're going to provide a method for analyzing the angle between two position vectors, if you will. We can also use the method that we're going to use today to understand how to calculate parallel force components in structural members. So therefore, I want to introduce the concept of parallel and actually perpendicular force components. But the method that we will look at today is really only meant to calculate parallel forces. And you will understand that as we move through it, because of our ultimate goal, which is to calculate these force components in actual structural members. So let's put that to an application, or first let's really talk about how to get there before we put it into application. And so therefore I want to introduce to you the scalar product. And the scalar product is a better name than what most of us actually know this by, which is called the dot product. The dot product is what we called it in high school, but I really like the term scalar product because it will always allow me to find the right magnitude. So this will tell me that this result here is never a vector. And the reason I say that is I often see that go wrong when students use this method. I ask them actually not to use the scalar product, but I ask them to find the parallel force component, and then somehow magically they come up with a vector. But if you memorize that this is called a scalar product, and scalar stands for just a single number, then you know that you have to come up with a magnitude and not with a vector. You can vectorize it, as I will show you later, but you by default will always find a magnitude and a magnitude only. So please keep that in mind, that we use this in this class just to find vector lengths, if you will. And not component. No components. But components are derived through other methods. So those other methods are just an extension of what we're going to do with the parallel force components or with the scalar product. So now let's talk about the definition of the actual scalar product, or the rules that we all learned in high school before. We probably remember this, but we should have it here anyways. So first of all, the scalar product is really defined, or the scalar product between A dot B, and so this is often written as A dot B, and that is defined as the product between A and B, or of A and B, precisely the magnitudes, and then multiplied by the cosine of the angle between those two. And the reason I left some space here is because it has to be the smaller angle between the two. So let me explain that a little better. So for that we have a short drawing here, or a small drawing. And let me draw two vectors, vector A if you will, and that is crossed by vector B. And now those two vectors have angles to them. So let's call this theta 1, and we call this theta 2. And when I ask the students in the classroom now, they tell me, clearly it's theta 1 because it must be the one between A and B here. And then I say, okay, that sounds good to me if you argue that way, but what really happens if I change the direction of A? So let's say I point A in the other direction, then the angle between those, according to the logic that the students give me, would be theta 2. And that cannot be true, really, according to the definition, because, spoiler alert, when we talk about the laws of operation, we will find that A dot B is equivalent to B dot A. And so theta 1 obviously is not as large as theta 2, and therefore that does not work. So it is not the angle between the two arrowheads that would be not true to the definition. It actually has to be the angle that is the smaller one of the two. And so the smaller one here would be theta 1, but that we will write down in a second. Let's first write down the actual law, which is A dot B is equal to A magnitude times B magnitude times the cosine of theta. And that theta, again, needs to be less than 90 degrees in 2D, of course. This is in 3D, this is a little bit different. But the concept here is easier to visualize in 3D. And this is a very important rule, so let's highlight it and let's memorize this. I will get back to this throughout the lecture today. So memorize A dot B is equal to A magnitude, B magnitude, cosine of the smaller angle between the two, here called cosine theta. So now we are ready to talk about the laws of operation, and I already gave you a small spoiler alert, but that law of operation is really called commutative law. So let's write that down, the commutative law. And that sounds fancy, but really all that says is that A dot B is nothing else than B dot A. That is defined that way, and you will see in a second why. And since we're talking here really about a multiplication, let's talk about multiplication with scalar next. You probably remember this from high school, that if you have a scalar A and you multiply it by A dot B, that this is equal to A multiplied by the vector, and then you dot it with B. Or likewise, it's also equal to A dot AB. So this is all the same, and that is the multiplication with scalars. That leads us to the distributive law. So this has something to do with how you do multiplication and addition. So distributive law, which states that if you have A vector and you dot it by B plus C vectors, that is nothing else than A dot B plus A dot C. So it's kind of like regular multiplications, if you want to think about it this way, like multiplication and addition. And so these rules apply no matter what you do with your vectors. And now I want you to think about this in terms of our base vectors. So remember that we had I, J, and K. So I, J, K hat. And those were our unit vectors. And if I write those in our old form, then remember that I is 1, 0, 0. J is 0, 1, 0. and k would be 0, 0, 1. And again, our old form that we don't use from now on anymore is this form. And remember the formula, right? Remember that a vector dot another vector, so a dot b is really equal to a magnitude b magnitude cosine of the angle between the two. And so now think about that, what that means for these vectors. What is the angle between them? They are defined by being mutually perpendicular to each other, and so the angle here is really 90 degrees. So the angle between them, so angle between I, J, K is really, for all of them, 90 degrees, right? And the cosine of 90 degrees is what? Is nothing else than 0. So in other words, if you have I dot j as the base vectors, you will find that that is actually equal to 0. And likewise, I dot j is also equal to 0, and j dot k would also be equal to 0. So now the question then is, what happens if you dot I, and here comes my expression, onto I itself? So I dot it onto each other, or actually, as I would call it properly, projected onto each other. So then you have an angle of 0 between the two, right? So the angle between these two would be 0, so theta would be equal to 0, and therefore the cosine of 0 is equal to 1. And then you find that I dot I is nothing else but 1. And that is an important concept to understand. And again, this goes actually back to our unit circle that is like listed in your very first lecture, where we didn't even have a video about because it's so basic, but please understand that it's derived from here. Similarly, j dot j, of course, is equal to 1, and k dot k is also equal to 1. And the reason I'm actually expanding on this is because I want you to understand what that means for a dot b. So remember that a dot b is actually defined as we did before. And you probably remember this formula from high school in a different way, or in an additional way, I should say. So you may remember this as ax, which we write as I hat, right? And ay j hat plus az k hat. And now I'm going to dot this onto bx I hat plus by j hat plus bz k hat. And now if I do what I learned in high school, where I combine the terms properly, I would be able to rewrite this as something like ax bx I hat dot I hat plus ax by times I dot j plus ax bz times I dot k. And that was the first multiplication, right? So if you want to think of this. So I took ax and multiplied it by bx. I took ax and multiplied it by by, and I took ax and bz. And so now this is like simply like multiplication, and I'm going to do the same for this component now and for this component, so I have them all multiplied through. I'm not going to write them all, but just to give you an example here. So then I would have plus aybx, and that would be j dot I, and then I have ayby, and this would be j dot j, and then I have A, Y, B, Z, and that would be J hat dot K hat. And I guess I'm just going to complete it now. So last but not least, I have AZ, BX, and that would be K dot I plus AZ, BY, K dot J plus AZ, BZ, and then K dot K. And so once again, what I did is just multiply it like we are used to from high school. And the reason I did this is because now I want to apply these rules up here. So I and j becomes 0, and j becomes 1, for example. So what does that mean for us? That means that this here now becomes 1. This becomes 0. This becomes 0. This becomes 0. This turns into 0. This turns into 1. This turns into 1. And then we have 0 and 0. And so what you will find now is that only in this case, because of the way I wrote it, the diagonal terms actually remain, right? So these terms remain, and that leads us to the formula that you know from high school, which is really nothing else than A dot B is equal to AX BX plus AY BY plus AZ BZ. And that, again, is another formula you definitely want to memorize. You probably already memorized this from before, but it is something that you need. And now I derived it for you, so you know where it comes from. And I will show you in a second why it's so useful for engineers. But again, highlight and memorize this. So this formula can be combined with our other formula. In fact, let's zoom out here and talk about the combination of those. So what I will do now is I will look at this formula together with this formula to find a useful application for engineers. But this is the laws of operation and the general concept for the scalar product.